I'd like to welcome you all to this webinar on PowerPad Plus 2001. We just wanted to run this because we've made some changes to the PowerPad for the 2021, and rather than hold those back for the official release of 2021 in a couple of months' time, we've actually implemented those into the existing software. So if you have a license for PowerPad and you have a February of 2021 license running, then you will automatically have all of these new features. So, introducing PowerPad 2021. So just moving forward, the MasterSeries, for those who don't know, is a massive product range of different applications, from big frame analysis to concrete design to retaining walls, pile caps, all of those different individual items and modules, and they can be purchased and used independently. So let's look at some solutions. We have created 4 solutions for you. One is the building design suite, the big stuff, not what we're going to be talking about today. The second is the PowerPad Plus. This is what we will be looking at. And the third is the Masterport Plus. We will again not be looking at that. And then finally, if none of those suit you, custom choose what components you need. But today we're going to look at this PowerPad Plus, and I'm going to go into it straight away. PowerPad Plus, or PowerPad we'll just call it, is not a little pro forma set of calculations. PowerPad Plus is a collection of our main programs with some limitations. So what are we looking at? We're looking at frame analysis, 2 and 3D frame analysis, up to 200 members now. So we've increased the capacity of that, and that is quite significant moving into the 3D environment. Portal frames, elastoplastic portal frame analysis and design of up to 3 bay portal frames. Simple beam analysis, so rather than using the big frame analysis, let's just use a wee simple beam. In this case, a wee 2-span beam with a cantilever. And obviously then the wind analysis, which wraps around the frame analysis to give you your integrated loading on your frame. So they're all part of the PowerPad Plus. With your frame analysis, you can go straight in and do your individual member design. Your rafters, your columns, your bracing members, all of that can be done inside your model. In this example, we are doing a haunched rafter. We're not doing it as a separate individual beam. We are doing it integrated into the analysis, pulling all the results out and choosing our member according to its unity values. Again, concrete frames, beams, columns and pad foundations. So we can see here we've got a plain frame, concrete frame. Connection design. So again, coming back to that steel frame, you can see that we're able to, in a fully integrated fashion, pull out those results and push them straight into the connection design. And likewise, timber, in this case a little attic extension done. Again, using the frame analysis and the timber design integrated together. We then have a series of standalone modules for doing masonry, freestanding walls, vertical walls with lateral loads on them, openings in those walls, retaining walls, concrete and plain masonry. Pile caps, that's a little 2-pile cap design, and composite beams. And finally, new for 2021, as well as increasing the number of members up to 200, we have added in finite element analysis. That will allow you to analyze a single FE surface, be it in this case a raft, or a transfer slab, or a piled slab. or even a flat slab, but it has to be below that large size of 200 square meters. So certainly for rafts, there's very few houses that will be 200 square meters or above. So that's a little run through, and just to reiterate what we're working on, just to confirm, what is the new facilities? So we've gone from 100 to 200 members. The wind analysis has again gone up to 200 members. Your integrated structural design in your frames, that's gone up to 200 members. And finally, your FEA, which was never part of the PowerPad, is now part of PowerPad to allow you to do those small rafts with openings, with holes in them, with cantilevers, whatever you want, where you want to work it. It's as long as it's a single FE surface, you can use that. And then all the other modules that we talked about there earlier. So let's get into the MasterSeries. So just looking at my license, I'm using a local key rather than a cloud, because the cloud licenses all our software. So rather than confusing people, I'm using a USB dongle just with the individual components. So PowerPad Plus with the limited facilities for all the different members and facilities as we talked about. So the first thing I want to look at is the frame analysis. The heart of the MasterSeries, the heart of the PowerPad system. So if we go into frames, we can have a quick look through the different types of frames that we can do. So here we are, PowerPad. So 3D frame, and we will be looking at that one in detail. This is in fact, I've just lost a picture of it. It's a first floor FEA slab. That's a raft, a domestic house raft. We've seen the attic frames and concrete frames. They're all very straightforward. There's another steel and concrete frame mixed together, because we can handle different materials, those three materials, steel, concrete and timber, all in the one model. This is a simple ground beam arrangement on piles, and we're using the area loading to distribute loads in one direction and in two directions. The more simple A-frames, and obviously simple beams, but a simple beam in this case with a few holes stuck through it, and continuous beams. We can also do the obscure, the fire escape extension out the back of an existing building. A nice little support structure there for fire escapes. Simple crank beams, and we can analyze that. And it's another concrete frame. A lifting gantry. All of these are all pretty standard. A portal frame with a mezzanine. This is done in the frame analysis rather than the portal frames. Towers in 2 and 3D, and then any types of trusses that you really fancy. And this is a timber purlin rotated through an angle, so we're going to get the biaxial bending on the member. So I'm going to come back and look at this drawing, and let's have a jolly good look at what we can do inside PowerPad. So loading the file, and here we go. What have we got? Well, we've got steel portals, and if I just change this from by section to material, we'll see that the green is the steel, the blue is the greeny blue is the concrete ground beams, and then these are the separate bracing members. So we've got steel and concrete in the one frame. So we've got possibly piles at the mid spans on these ground beams, plus at the column supports around the structure. And if we can just turn on the 3D, we'll see that that's exactly what we have. We have all these little supports sitting around there. Turn off the 3D, you'll see all those supports sitting around. And turn that off. Now, we also have in this structure primary and secondary members. We have members that have got openings in them, distinct openings and repetitive openings. We even have plate girders, all in the one frame. So if I was to look at this and I want to, for example, introduce a couple of additional members, I'm going to put some bracing down through this face. First of all, let's check we're not going to overcook the books, so to speak. So we are only at 146 members. That's not a problem. So I'm going to go in to create, and rather than creating members, I'm going to create bracing. And I'm going to create CHS, and it's going to be 88 by 9s, and it's going to be repetitive back and front. And I'm going to do that as bracing from there up to there, and there we go. Start, finish, start, finish. And those members add it in very simply. Now I'm going to add in another couple of trimmers, because you can see here we've got that was between nodes. If I come along and create some members to trim this out, so let's add in some general members, and I'm going to choose a member that I've already used. So let's have a wee look at what have I been playing with. Oh, quite a few. Maybe a wee bit light. Actually, no, the 127 by 73 will be sufficient for what I want to do. So I'm going to come along here, and I'm just going to move across, and as you can see, I'm getting exact distances, and then come across, and I've just been playing around. I accidentally clicked there, so I just press escape. I'm free again, so crosshair, and I can say I want to go 2.125. So rather than the 250 steps, I can go my exact distance, and then I can come straight perpendicular to this other little member. And there we go, we've put a trimmer in there. So very simple to add members, very simple to take them out by draw them in again. You know, clearly this member is coming right in, right beside that. It's been drawn to the top of the member, but it's not infringing on the other member. Otherwise, we would have seen its profile coming poking through the circular hollow section. As you can see, we can see right through these. These aren't just little white circles; they are open for you to view through, so we can see the other members through each other. So no, we're not infringing on that opening in doing that. Now, definition of members is very straightforward. Loading is again very straightforward. We do have a 3D structure, so we're perfectly entitled to come along and say that my 3 floors, ground, first and second, and eaves have these different loading on them, and I can even specify slab thickness. What else can I do? I can come along and I can then say, let's put on our area loading, let's put on our floor loading. So we can define panels. In fact, we do need to define a panel because we need to add in this little trimmer here. So I'm going to come along and I'm going to say, on this surface, I want you to add in that as an additional surface, now spanning the same direction, or you might decide that you want that one to span the opposite direction, because it's just a wee infill and it's going to be precast. So what I can do is I can say make a local change, and I am going to change the span of this surface, and now it's facing the other direction. So I've got all those, and you might take over to this surface. Whoops, sorry, that was clicking on surfaces rather than members, and change around, make local change to that surface, change the span, the other direction. And we can change the others. As you can see, some of these have already been changed as well, and you could also say let's copy that to that one, let's copy it to that one and to that one, so they're now all spanning correctly. And we even made that one two-way spanning just because we can, and it's all fun and games. And likewise, we don't have any panel out here, so let us turn off the make change and add in the additional part here. And again, I'm going to make that span the opposite direction. So that's now spanning the opposite direction. And that's how simple it is. We can also apply line loads, and we can apply patch loads onto the surface. If I come back and look at my loads, line loads, yep, we've put all of these line loads onto the structure at first and second, ground and second floor, ground and first floor, whichever way you want to talk about it. So they've all been applied, and obviously for some reason we decided that we weren't going to put a load in at this area, because whatever reason, it may be just lightweight glazing across there rather than the full, and again over here. And we can come in and we can correct that and add those in very, very simply. We're dealing with this set of loads, and we can just say select, and we've applied it to those members because those were on member loads. And likewise, we probably should have something around the back as well. So that was on member. You can see we can have off member loading as well. So if I go internal walls, you'll see there's an internal wall extension. We have all the different stair loads and all the different loads applied to that structure. Very straightforward, very powerful, very flexible. So that's your dead and live loading applied. Patch loads, point loads as well. What we also now want to look at is wind panels. First thing I'm going to talk about is wind directions. I'm going to say give me 4 directions because it's a slightly skew building. Let's look at it in all 4 directions. And because it can be open, let's look at it with internal pressure, suction and pressure. So that's going to triple up the number of wind loading cases. We're going to go for directional method with UK factors, and we're going to use the wind analysis. So what we're going to be doing is we're coming along very straightforward into our site, and we're saying where is this building, and it is down, looks to be pretty much south of Greater London. I'm sure there's a town down there we could pick, but if we unlock the town, we could go to somewhere like Croydon, which is slightly further in, slightly more dense. So we're now in Croydon, and we've got our wind. We can take all our National Grid references or our east things and northings for you. A National Grid references, brilliant website called Grid Reference Finder. Type in a postcode and it will give you the grid reference, and off you go. And it's not Athlone anymore, it's Croydon. Just as a reference, Croydon Town Centre. And we're using the full GB, we're using the UK factor, so we know the orientation of our building, and we're taking the dominant wind from the west by southwest. That is our dominant wind direction in this case. So it's very important we have the building orientation correct. We can rotate that. I'm just going to leave it as it is. Topography is very straightforward, and our fetches and our reports, and we can see that we should be able in here to, if we wanted to, rotate the building and everything. I'm using the Eurocode, and that is it. That's the first half. The other half is putting the wrapper on the building. So let's look at the wind loading panels. The panels themselves, again, also simple and to apply. In this case, horizontal and two-way spanning. and again one-way spanning, and ignoring the bracing members. It knows that any member that's called a bracing member should not be used for support. And we can see all of our lovely surfaces defined here, very straightforward. And I'm just going to close that. So what does that give you? Well, we've seen the gravity loading and the loading that comes from that. What we want to see is what we'll be analysing anyway, what the results are for the wind. And here we go, we can see from each of our wind directions, and I actually put this additional member in earlier because it wasn't there, just to stabilize that up. So I do need to correct this panel. So let's go back, loads, wind panels. That's it, we're after this one. And what we now need to do is to get these members included. So in apply mode, we're going to add that and that into that member, and again spanning horizontally, and that will give us our completed wind structure. So we have our wind pressures, that's better, and it's for each wind direction, so we can choose the direction we want to consider it from, and that's all good. Now we just analyze, nothing to it but do a static analysis of our 120 cases. It's been very over ambitious in that it's looking at the pressure in each direction. It's looking at the pressure with suction and the pressure with pressure. So it's doing 3 times the cases. We're also looking at dead plus live plus wind, where the wind is the dominant and where the live is the dominant. So that is why we get so many loading cases, but that does not matter. It's a computer. Let's just go and space frame that out. Okay, that's our analysis done. Let's turn off the pretty picture. Let's turn off the 3D. Let's go into results. Let's look at our graphical results. What have we got? Well, you've got your bending moments, and of course those are going to be of totally different scales for the different types of members. Those internal beams without columns underneath them, plate girders by anybody's means, are going to have far bigger moments than anything else. But you do have the portalization occurring. Now what I always recommend is you put it in plan, you turn on deflections, you can see the movement now. Don't panic, that movement's magnified up 50 times, and it is ultimate. So coming down on a 1-to-1 we have no movement. That's better. Now let's look at our whole structure. Service cases. It's going to think for a second. It's going to draw them all over each other. And I know that if I went to 20, you get a whole series of different local bendings. But you know, that's just the portalization pushing out, as you would expect. And we'll pull that back down to 1 in 1. 1 on 1, we can see no realistic movement. The structure is stable. So we're happy. So without any further ado, we can go in and we can design this. Now we're going to go in and do the steel design, but before we do that, we're going to have a quick look at something called member groups. This allows me to take members, these 6 rafters, and group them together and say, yes, when you design the one, you design them all. We look at our external columns. When you design one, you design them all. We look at our bracing members. You design one, you design them all. Same size as well. Keep it simple. So I've done a whole lot of design groups, and that makes my life and your life so much easier in the steel design. It's automatically created all the design checks, apart from that one there and these 2 bracing ones, which we never did. And we can add those in at any stage. So it's not looking at one, it's looking at all 6. And what I mean by that is, if I look at this column, that's working, but I just know that this one down here, one of these ones at the back, is a wee bit unhappy, and I think it might be one of these. I think putting that vertical in there has now made it work, but not to worry. If I took this Okay, I'm already at the 15223, so I want the light section. If I went to this one and reduced it down just, for example, to a 235 grade of steel, that's just working and no more. But down here it's not going to work. So if I was on this member or on this member, no, let's take it back to that one. I might not know that the others don't work, but that little hook, that little grouping allows me to size not just the one member, but all 2, 4, 6, 8, 10, 12, 14, 16 plus 1, 17 members. So when I go auto size, it's size not one, but all of them. And it tells us, because of the very light grade of steel, we need to go up to the 30 kilograms rather than the 23. So very, very useful. And if I take this back to 355, auto size again, we will see that there is one of the members is requiring the 30 kilogram anyway. But you get the point. I had it down at the 23 and it's working. I auto size and it suddenly says 30 because it's checking not the one member but all 17 of them. Likewise for your rafters, you've got the axial with moment, but you've also then got the appendix G checks. Oh, sorry, just clicking too fast. There we go. It's Eurocode speak, so we are appendix BB. And we've already seemed to have put a stay out here and assuming that this portion is going to work. So your very detailed design. So let's look at a few of the members that are failing. And how do I know what's failing? Let's scan for failures. It's going to tell me how many members are currently failing for the current section sizes. And I should have a couple, unless I've mysteriously fixed this, which I don't think I have. Here we go. Yep, I thought I would have 10 failures at least. 10 or 12. 12. Good guess. So 13 failures. Now what it's going to do is allow me to show the unity values in every member, which is a wee bit over TT. You have to go and try and find the ones that fail. But I can say, no, only show me the failing members. So I can see this column is failing just by 2%. This welded plate girder is fading, and it's failing on deflections. So what I want to do at the minute, it's checking it over 1/360. Now 1/360 is fine, but possibly not for all loading cases. So what I might consider is coming along and changing that limit to 1, and it's now checking it against dead and live, which is not very clever. So what I'm going to do now, it's closer to working. I'm actually going to go into the table and say that live load only is 360, dead and live is 250. That's fine, and the rest I'm not interested in. So I know that I now have a better idea of the member, but it still is failing in deflection. So what do I need to do? Well, in this case you need a bigger section, Tommy. So let's go back to the plate and we can see it is, we can squeeze it out to 600. Just type that in, 60. We're still failing. We're going to increase the web to 15 and we're still failing. And the top and bottom plates will keep at 300, but will increase the thickness to 20 mil. So 15 web and 20 mil flanges will work. And we can also see that the 6 mil fillet weld provided each side is enough to design the weld on those plate girders. So again, a very intensive tool. So we can design our members, we can print our members, we can even do auto design on all the members and see what happens. I could take, for example, this column and just say, ooh, it's a 40 kilogram, and I'm going to go by weight order, so it's the lightest, and size it up, and it's now found the 356 by 45 is enough to make that work. Now, correctly, we do need to reanalyze because that's an indeterminate member. Moment fixed to the others, so there will be a bit of a kickover, so I can just go and say reanalyze quickly, Tommy. Yes, keep going. 1, 2, 20, 30, 40, 50. It's counting down here, by the way. Half them done. I wouldn't even have the title of the first one written, never mind, I designed it by this stage. And we can see that when we do, it needs to update that scan, and it will now tell us that that member should no longer be failing. Minish is asking, is the weld on the plate girder a new feature? Yes, it is. It was released just with this 20. We didn't hold it back for the full 2021 release. As long as you have a 2021 maintenance and you're using a February version, it will do it. So now we don't have, that one's now no longer failing because we fixed that. That's good. And that one's no longer failing because we fixed that. And we can walk around and do that for each of these types of members, or we could just go and do everything at once. For a building this size, I prefer to do them in their individual groups and sort those out. But I'm just going to come out of that. I'm not going to spend all of my hour here, which I am using up. Now, I can also design the connections. Yep, so here we go. Here's our rafter that's coming through. A little rafter, and we're checking it, and we can see that it is working for this load case. So we're going to check this brief for all loading cases in case there's a reversal case that gives us forces that are higher, or higher in reversal that makes it fail, and it's not. It is perfectly good. The brief is fine. We can look at this simple construction, and there's a few warnings. It's I suspect it does not like one of the plate sizes is a bit small. We just need to extend that. There's also, so those two plates need to be a bit bigger. We can make it bigger with set bigger, wider bolts, but we'll not worry about that at the moment. This is, I believe, a bracing member. Yep, we've done the full bracing connection and extended the end plate, and we're just doing several different dirty connection types, all in that process. And finally, over here, we have our base plate, and we have a wee compression problem at this moment, but we haven't probably told it what the concrete is. Concrete grade is that. Cube strength of the grout is 15. That's okay. But we really want to make the whole concrete pad bigger. So if I turn around and I say the edge of the concrete is at least 300 away, and the depth of the concrete is at least 300, it begins to improve things, but we still need a bigger compression zone for our base plate. So let's get back to the plate, and we just click on the plate to go to its input, and we can say, well, maybe make that 450. That's going to give us just enough to take the full effective area that we need. We could probably go right in line with 425 or 420, and that works. And again, we'll just check that on the brief, and there are no loading cases that require anything larger than what we've done, and it's fine. So you have fully integrated steel and connection. But we just didn't have that. We also had concrete beams. So let's just go straight in and do our concrete beams. And it's just warning about the direction of that one member, which is not a problem. And if I look at any of these beams, it's got a little failure here and here because we have a pile under the middle of this to separate the the span out, because it's all on piles. Otherwise, why would you have ground beams? So it's all on piles. So these need to be sorted. It's failing. We could go up to 25s, or we could go for 5 bars, but an alternative to that is very simple: to come along and say, right, left hand side, let us pop ourselves in a 10% redistribution, and likewise on the other side, just to make it right, pardon the pun, a 10% redistribution. And you can see now we've got our elastic line and our redistributed line, plus for Eurocode the shear drag that we get on the design. So we've actually been able to use the smaller 20s. And could we get away with 16s in the bottom? No, we couldn't. So it's 20s. You could be pernickety and say, well, could I go for 2 16s and 2 20s? And we could split that into 2 bars and then reduce one. So we could go for 2 20s and 2 16s. Steel fixture's not going to thank you for it, and it's not worth it. So I would just take that back down to 0, and then that using right mouse and left mouse up to 4 bars. For very simple, concrete design, all included in your frames. Now, I mentioned that we have FE analysis, so let's look at what we can do in FE analysis for rafts, for transfer slabs. And this is one I put together this morning. And basically it was actually a bigger model with concrete walls underneath, but instead I replaced some of the concrete walls with line supports, because we're only allowed one surface in this program. But still, if I go to restraints and I go to surface restraints, we will see that we, as well as all the columns, we have here, 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 and here, and here. So if I put this in the top view, we can see that wall there, a wall there, and 2 walls back there, because you don't have columns underneath. We don't have columns underneath here and here. So we're going to have big problems around here, and we've nice wee cantilevers and everything. So all very straightforward, except the guy did load it up quite heavily with point loads in different places and line loads and the likes. So I'm just going to go straight into my results and graphical. That's going to ask me to reanalyze this frame as a space frame, and again, not taking long enough, long at all. And you'll be glad to know, if you're already a user of our Finite elements, that the 2021 official version coming out in May will have an even faster processor for doing FE surfaces. I won't go into it, I'll just say it's a lot faster. You'll notice that we have an adaptive mesh that has been refined to be more dense around all our nodal points, inner and internal and edge nodal points. And we look at our bending moments, and all we're getting is our beams. And let's just pull these down, and you'll see some flexural here and here that's coming through from the walls below, and you know, plus and minuses here and here and here and here, as you expect. You can also look at your deflections, and you'll see the deflected shape, and we can magnify that. Whoops, maybe not up that high, and you can see the whole panel going down. But that is really still looking not at those elements, but at the main line members. So let's go into shell elements. And if we look at our Y displacements, we can see where we have a support wall here and here, and nothing in here. We get the maximum displacement on the wall, so on the slab, and we also have then an uplift here. If we look at our wood and armor moments, we can see where all the moments are coming to, and there's a massive take up here and here under these point loads. So we can also turn around and say to it, you know, really, let's take out some of those erroneous values and let's go for a maximum of, say, well, the 200's fine. Let's go for a minimum of minus 200. And we're going to go for 30 rather than 15 and apply. And you'll now see that we're getting a more detailed set of forces coming through. Naturally, where we had the hugging here and here, we don't have it, but you can see more detailed. And that's all very interesting. Wooden armor MX. Let's look at the MY, opposite direction, and we can see the detailed, one's sagging, one's hugging. I think that's the wall, so that's the hugging, and that's the point load, so that's the sagging area. And that's also a point load giving us a sagging area. So we can see the values coming through, and what we can also see is our areas of steel. So let's look at our bottom steel, YY, and we're going to go for, it's a floating slab, it's not on the ground, so we'll go for 50. Although we could argue that, sorry, that's the separation of the bar diameters, so we'll go for 50 for the other direction. The YY is the lower, and we're going to go for, EC2, and we'll go for 500B and 30 concrete. And it's now going to come along and show us what reinforcements. So generally we're going to get away with 16s at 150. That's 7, I think it's 750 is the rebar, 740 something. And then we're jumping up, so we'll need additional around there. And we will need to reinforce that. And obviously we can work through that. And that's the YY. And if we look at the XX, again, we do need some heavier reinforcement around here. So this slab itself may need to be thickened, or we may need to go for heavier reinforcement in these areas. When we get to the top steel, obviously that's going to be a lot less displayed, and we'll see that, it's saying around these we're needing drastic amounts, but we can spread that out. We can use our, so what we want to do is to take a line down through this part of the slab, but before I do that I'm just going to rotate it into isometric view, otherwise we could have been clicking on the top nodes rather than the physical nodes. So I'm going to add a line diagram starting at that node, ending over here, and I am going to do it as a wooden armor y-axis moment and apply. And there we go. And if we look closely, we'll see we're up to 309 kilonewton meters, 310 kilonewton meters. Now we can relax that by asking to do a strip average, and I'm going to average over 1 meter width, and we'll see that that comes down to 260. So we're reducing from 300 to 260. That's a 40, which is a 10-15% reduction in peak moments, and we can use these tools to more accurately size up our reinforcement in our peak areas. Just to show you what happens if I come along and I take a second one from this node all the way across to this node, and again I'm going to average it over 1 meter and apply. You see it's a lot less, so it's only over that, and we can actually ask to show all, so we can see the difference between the support at the edge of the wall and obviously the point load coming down there, as against to 1 meter away from it with much smaller values. And that gets us a nicer set of diagrams, and we can just tidy that up a wee bit while we're here by asking it not to draw the mesh itself. So that gives us a wee bit of a tidier set of results. Naturally this is not running perpendicular because this this isn't the same width as this, but it is close enough. I could reenact that second point by applying it roughly over here, and that's a bit more respectable. Or I could take it to the next point out, and there we go, a more perpendicular parallel orientation, and you can see the variance between the two sets of data of your bending moment diagram. So that's all part of the PowerPad system. We'll look at the raft and then we'll go into what else the MasterSeries PowerPad can do, because really what we wanted to show you today was the extended capabilities of the analysis and the FEA surface on that. And I'm not sure I want to even go back into that existing frame with the 750 meters instead of millimeters set on the strip averaging, because before I edit it, it's going to try and redo it. So it's having fun. It's thinking my license is still locked out, but that shouldn't be the case. It should get through. While that's doing that, I'll have a wee quick look at questions. Somebody's asking, is panel loading available in PowerPad? Yeah, panel loading as an area loading, absolutely, Bruce. That's been available for a few years now. So yeah, absolutely. Okay, let's go in and look at my other little piece of FEA, just to give you an idea of the more realistic design. And yeah, that's the one. It's a little house extension with different loading on the two floors. Or I should want to say on the this is two-story area and this is one story, so the loading coming around it is higher, spanning that direction than that, and then obviously there's a big wall at the back. So it's interesting, plus a couple of point loads. So that was very easily done in the system. So this has got the subgrid modulus for your soil properties, because this is a raft, and therefore with subgrid modulus you're doing a more iterative process in your analysis. In case you're wondering why a smaller frame is taking longer to analyze with only 12 loading cases, it's because it's having to work out what's in tension and what's not in tension, and reiterate on that process. Very intelligent people develop this, so that gives you the pressures you want. So it does all depend on the subgrade modulus you choose. And just while that's finishing off, there's a very good article publication that I normally fire up from my links. It's either here or it's in engineering. There it is. It tells you about subgrade modulus and bearing pressures, friction. We've gone too far. Here we go. Values of subgrade modulus, subgrade. So you can see we're talking telephone numbers, the tens of thousands. Clays can be anything from 10 to 120,000. We do recommend that you choose something in between. You don't go too hard or too soft, and it's very, very useful. So here's our analysis. Let's look at our shell elements. This is our areas of steel required, top XX means the bars that are running horizontally, so we can see that we can get away with the 393 mesh in this bottom area everywhere. Happy. On the top we can get away with possibly a bit more than the 393 is required in these areas. Yeah, it is. So you're going to need a bit more in the YY. So those are all very, very useful for you in designing your slabs. What you also have then is, what is the pressure? What is the reaction? And we can see that in here we're only taking 20 newtons, and down out here we're up to 140, 130. So we can see in some small areas on the corners we're really going above the 100, and that is all to do with, and the massive big line load at the back here is pushing this up, and we should be able to place a point on this. Yep. So we're up to 100, 100, and then down to 89. So I'm happy. Obviously that's the ultimate. We would prefer to be looking at the serviceability of all spans loaded, and that's going to give us values that are well below the 100. So that raft would work at 100 kilonewtons per meter square. As you can see, it's not a even distribution of your reactions, and likewise the opposite of that, your displacements for deflections. So very useful little tool, very, very useful little tool for doing your rafts and your small transfer slabs or small flat slabs. But that's not everything that PowerPad is. We've only covered a small portion. PowerPad will allow us to do masonry walls. So let's look at a masonry wall in PowerPad. And what have we got? That'll not work. Somebody's playing around. And this won't work because there's too many openings. And it's going to get very annoyed. And it's just taking the openings off because there's too many of them. So we cannot use the advanced yield line in PowerPad. But we can go to openings and we can take out one of the two openings. And if we take that opening out, we now can work. So we can use the sub-panel method for designing our walls that have two openings in them. So there's no problem there, and we can work away with that. And we can either use the simplified method of smaller effective widths, or in this case it is using the sub-panel method. We can see that it's failing miserably on this, as one would expect. So, but you do have some great tools in here for doing your walls in the PowerPad. If I was to go to retaining walls, again a simple reinforced concrete retaining wall with a prop at the base, so it's not sliding for whatever reason. If I go into the wall data, I can see my dimensions. If I go to loads and props, that's it, take out the prop at base, we'll see that the thing is now sliding horizontally because the surcharge and everything is pushing this. We'd need longer base. If we were in British standards, we could wing it with a wee bit of cohesion on the base. We can't do that. We can put cohesion into our soil, but I'm always very skeptical about doing that because the main soil may have cohesion, but anything you backfill with, unless you're going to put clay back in again and consolidate it and compact it, it's not going to do it. So you really need to prop this, in this case, with a prop at base, and that's your wall designed. Very simple and very straightforward. What else have you got? Well, you got little simple pile caps. You also have little beam designers, and these are a alternative to using the full frame analysis for doing your simple beams. So you can just take a wee beam, one span, two spans, up to three spans, and you can design those very straightforward and go in and take that cantilever and just go through and do your design. Very straightforward. Again, it's only an alternative to using the big frame analysis. And the other trick that we have that a lot of people miss is that you have fully fledged 3-span portal frame analysis and design. So what have we got? Portal 2. I wonder why it's called 2. It's got 2 spans and they're not at the same height. So two spans at the same height, we can go in and we can analyze that elastically first, I always say, and then into design, steel design, and we can see that with elastic it's overstressing. So what we're going to do is we're going to analyze it plastically now. We're going to do a plastic analysis, and we've formed our hinges correctly, and we've now got this up to the underside at the sweet spot. Our rafters now obviously have sagged a bit, and we do really need to fix those, and there's lovely tools for doing that. And if I go into my detailed designs, I can look at my rafter and say, yeah, that's a bit much. That's all okay, so we need to change this. We're using a 533 by 82, and we're using a 457, and we really need to up the strength of that. Somebody's put in 235 instead of 355. That's a lot better, and that's, I'll just do a quick plastic analysis, and we should come up with maybe one hinge, and everything should now look a lot sweeter. There we go, that's fine. And we can see that we would need to put a stay here all the way up to there, and we'll see that we need to stay up to the fourth sheeting rail up. Rafter wise, that's still on satisfactory, so we'll need to stay out to there. That's okay. If I take that out, that's fine. So that's showing me that I would need that stay at the third purlin point. So eaves 1, 2, put the stay out there. And that's your portal, and it's very similar to the master frame. It's very, very flexible and powerful, but it is elastoplastic analysis and naturally designed. So I'm just going to walk through a few of the questions. Can we use the wind in other countries? Yes, you can, but you would need to use input your own Q value for your basic wind pressure. Can you show global deflections? Absolutely. Even in here, if I was to go to output and view graphical, when you're looking at deflections, we can look at the y-axis deflections. So that's the nodal displacement, obviously under dead plus live, 300 millimeters. Let's put that in the context at a 1-to-1 and make a Y-frame. It's not as big a movement, but yes, it's a portal, of course, so it's going to move down vertically. And if we come into the eaves and we show the member X displacement, you'll see the 38 mil horizontal push out. Now what you also have to understand is when you're dealing with a rafter, as well as the nodal displacement, you can have the in-member displacement, which is used generally in member design. And that is a lot less than this, because the 300 mil, actually if you zoom up and I magnify this, maybe not as much as that, what you're doing is you're taking a straight line from here across to here, and then this 39 is the maximum from that. And that's very useful in multi-story and things like that, because you know you're not interested in the top floor having all compressed by 150 mil due to the column shrinkage. You're interested in the curvature of the beam for your services. So yes, we do both. Does it have British standard? Absolutely, you can go for British standard on all of our software. How many degrees of freedom in each node? Well, for our general beam elements, you're talking about 6 degrees of freedom, 3 directional and 3 rotational. When you're talking about the FE analysis, we're talking about 8 noded quadrilateral shell elements, so the more accurate quadrilateral elements are used in your analysis. That's about it, ladies and gentlemen. I'd like to thank you all for coming along. One last thing before we go, or two last things. One is learning the software. The MasterSeries comes with a multitude of learning tools. So you have resources, you have videos, you have manuals and tutorials. Manuals, yeah, they're there and they're very detailed, but they're awfully boring. Tutorials, they're great. You know, simple steel frame design or a 2D steel structure is a great starting PDF. Doing a wee plane frame with loading directly onto it, or let's go and do this as a 3D structure. Again, similar frame, but it's 3D with primary and secondary beams spanning in all directions and area loading and stuff like that. Very great tutorials. You also then have, as I say, all these videos, and the videos are available either on Vimeo, MasterSeries, or straight through the software coming along. As you can see, we do recordings of different videos, and there was one on rafts and piles and things like that, and thermal load on members. That's an interesting one. So great resources. To try the software, all you do is you just go start your trial, put in your details. We're going to be living in Montserrat, and this will be me. And next, I am a steel fabricator, and I am only interested in portal frames, or I want the PowerPad. So you can choose more than one. So PowerPad and full pile caps or full retaining walls, if that's what you want, and then submit, and you will get a link to download a 14-day trial on the software. So ladies and gentlemen, I'd like to thank you all for coming. Stay safe, and any questions, just contact myself, Tommy at MasterSeries.com, very simple, or my colleague Andras at MasterSeries.com. All the best now, and thank you for attending.